Welcome back to Quad Drone Lab. Let's jump right into part 2 of our drone battery explainer. Today, we're cutting through the marketing fluff and looking at the hard physics of internal resistance versus those wild C-rating claims. For the researchers, professors, and pros tuning in, this is all about what literally happens inside your power architectures under extreme load.
Here's our roadmap for this explainer. We'll start with the LiPo versus Li-Ion basics, break down internal resistance, calculate some realistic C ratings, dive into heat and thermal runaway, look at cooling solutions, and wrap up with the semi-solid state future.
Okay, section 1, LiPo versus Li-Ion basics. This is the absolute foundation of flight. It all really boils down to this classic trade-off, energy versus power. On one hand, you've got lithium-ion. These packs give you massive energy density. We're talking up to 60% more capacity, which is incredible for endurance. But lithium polymer, or LiPo, that's your muscle. LiPos deliver those instantaneous, massive power bursts you absolutely need for multi-rotor agility. So how does that play out in the field? Well, if you're running an FPV racing drone pulling insane 100C+ discharge spikes, or you're hauling a heavy cinematic rig, LiPo is practically your only option. You need that punch. But if you're engineering a long-range surveillance platform that needs to stay airborne for over an hour, or you're doing steady mapping and delivery operations, Li-Ion is totally the way to go. Moving on to section 2, let's talk about internal resistance, or what I like to call electrical friction. Think of DC internal resistance, or DCIR, literally as friction. Every time you jam the throttle, this resistance stubbornly fights the flow of direct current. If you're just hovering gently, it's no big deal. But under high load, this electrical friction robs your drone of precious stored energy, converting it straight into useless and honestly dangerous heat. I love this quote from John Salt over at RC Helicopter Fun. He says, "Just think of it in the same context as putting a big stinking resistor between your battery and your ESC or motor. That hits the nail on the head. You are basically forcing a voltage drop that starves your motors right when they're begging for power." So what numbers should you actually be looking for? Well, a brand new industrial cell should sit nicely below 1.5 milliohms. As it ages, it'll creep up to that 3 to 5 milliohm range, and you'll definitely start feeling some voltage sap. But, and this is absolutely crucial, if the cell crosses that 8 milliohm threshold, retire it immediately. The heat generation at that point is critically unsafe. Right, into section 3, calculating realistic C ratings. This is where marketing collides with actual physics. Let's debunk some of those impossible manufacturer claims, shall we? You can calculate the true continuous discharge limit yourself. It's just 3 steps. First, multiply your pack's capacity by the highest IR reading of its cells. Next, take the square root of that number. Finally, divide 2500 by that square root. Boom, you now have a scientifically sound continuous C rating.
And when you actually run those numbers, the results are wild. Let's say you have a 5100 milliamp hour pack with a pristine 1.4 milliohm resistance. The marketing label might scream 130C, but mathematically, it maxes out safely at exactly 30C. Yep, 30C. Anyone claiming standard chemistries can safely push continuous rates much above 40C is frankly bending the laws of physics. So what happens if you just ignore those limits? Your high internal resistance triggers severe voltage sag. Your motors get sluggish, your flight times completely tank, and all that wasted energy turns into heat. That's when your battery pouch starts swelling or puffing. If you see a puffy battery, that's a very clear physical warning that its internal structure is severely compromised.
Which perfectly leads us into section 4, heat and thermal runaway. Let's map out the sequence of a disaster.
For the researchers tuning in, you probably know Bernardi's heat equations. If you've ever plugged these variables into your Python simulation code, you know total heat generation is a mix of reversible entropy changes and irreversible polarization. But when your drone is tearing through the sky at high speeds, it's that irreversible ohmic heat driven straight by electrical friction that completely dominates the thermal load. And that heat triggers a terrifying chain reaction. Watch how fast this escalates. At 85 degrees Celsius, the solid electrolyte interface breaks down and starts generating its own heat. By 140 degrees, the internal separator just melts. That causes massive short circuits, and suddenly you're rocketing up to 500 degrees Celsius in full-blown catastrophic thermal runaway. Okay, section 5, cooling and thermal management.
how do we actually engineer solutions to stop that?
Enter the smart BMS, the battery management system. This is the absolute brain of the operation. It's constantly monitoring your thermal conditions, actively balancing cells, and strictly governing the current you can draw during aggressive maneuvers. Basically, a smart BMS steps in to enforce voltage thresholds before you ever reach that first dangerous temperature spike.
Of course, mechanical cooling plays a huge role too, but it's all about trade-offs. Natural convection, zero weight penalty, but low efficiency. Forced air cooling is a great middle ground, especially for ag drones. But as we start scaling up to heavy-duty passenger eVTOLs, engineers are realizing we literally have to use liquid cooling plates, despite the massive weight penalty, just to handle the thermal load.
You know, simply choosing the right capacity is a thermal management strategy in itself. Check this out. On a 6S system under full throttle, jumping from a 2600 mAh pack up to a 5000 mAh pack cuts your voltage sag in half, from an alarming 4.8 volt drop down to a much safer 2.4 volts. It dramatically reduces the thermal stress on your cells.
Finally, Section 6, the semi-solid state future. It's time to re-engineer the chemistry.
This is a real game changer. Semi-solid state batteries are replacing volatile liquid electrolytes with a non-flammable gel. This inherently resists thermal runaway, and it suppresses that microscopic dendrite growth, meaning these cells can survive over 1,200 cycles. Plus, they're breaking the 350 watt-hour per kilogram barrier. And they even hold 92% of their capacity at negative 30 degrees Celsius. It completely solves the traditional LiPo bottlenecks.
And hey, if you want to stay ahead of engineering curves like this, we'd love for you to join our YouTube channel membership here at Quad Drone Lab. Your support directly funds our research mission, allowing us to keep distilling this complex aerospace data into real, actionable insights for the pro UAV community.
So I'll leave you with this provocative thought for your next design review. As we push the boundaries from delivery drones all the way to passenger transport, is your power architecture just blindly chasing energy density, or is it mathematically engineered to survive the heat of internal resistance? Thanks for joining this explainer, and we'll see you in the next one.